summation to part of this video, and then it's going to be another summation in it also. But let's talk about my summation intent. My intent is to help engineers understand that the cracks are not random, that they're not just random aggregates that causes the crack. Now, if you were to find one crack, and that is one little spalling, I would say that that one spot could be a random stone issue, and there is that stone causing it. With that said, let's go the opposite. Let's go with Latitude's position, and awesomely, I'm glad he did it. Latitude, his background is a civil engineer, and he knows aggregate as pretty much ACI. That you must concrete as you must use ACI pretty much. You must use these mix, this and that. Well, with that said, using those mix, and I'm not an ACI fan. I do like some of their research, but I'm not an ACI fan because they make concrete that cracks. They say it's just random. I say it's bad engineering, and I'm going to show you. It's all going to be seen. Bad engineering, number one, with using angular stone. Let's go ahead and work. That's pretty much my summation. That's where it's going to go over the many videos to come. And you'll see now, you'll never be an angular stone lever again, unless you're trying to make a system that cracks. Okay. P.S. He wrote the part of this. Let's just jump into that. Take a look, and I have the link open over here. We'll get to it. Indicates, as per my comments, I think you have misunderstood cracking. Yes, it is random, as they are affected by the position of random spacing of aggregate. Affected by the random spacing of aggregate. So let me open this. Let me bounce back and forth. Okay, guys. I lay down these stones. I want to jump. We'll play this video, but I need to jump into this random. Let's use this as the randomness. So let's find this randomness here of these three angular stones. 1, 2, 3, and I can't count. Of a weakness in the concrete. All right. We all would say that if the stones were to line up like this, you don't have any paste in there, and you only had, say, 4 inches, and this is 3 inches. You only got a ½ inch of paste between the base and all of these stones in here. You created a weak spot. The problem is with this theory that he's going to state to me is that this means that this would have to line up. I'm going to cut to the chase to be a mistake here, a mistake here, a mistake here, and it just keeps going on. And the mistake, ironically, I'm using the wrong word, facetiously, all is in this line. And why didn't the mistake just start going everywhere? Well, because the mistake or the randomness is not really random. Yes, it is random, as they're affected by the position of random spacing of aggregate. All right, so the spacing of aggregate is kind of random. We mix it up. We know it can't really be really random, because then you can't get consistent concrete. So part of your statement is true, and part of it is just prove that we can do cutaways of concrete, and it looks pretty damn consistent, the randomness, if you will. The blend looks pretty damn consistent. So we don't get, multiple stones stacking on top of each other typically. They pretty much get all fluid around them, paste around them. They're pretty good. It's pretty randomly nice. Since you're going to say random, it's mixed, and that mixed along with your paste and fluid gets you a nice rotation like that. If I were to mix nothing but stone, I get a random direction of stone, just mixing it in a tumbler and then come to a stop. I add paste to it and mix, and it comes out pretty consistent with the mix. The blend is pretty consistent. Again, we can do PSI testing and see that. And so I find this random thing is kind of contrary to random, right? All right, it's like baking a cake. All this stuff is blended, and it mixes pretty damn well. Well, that's just how mixing works. Cracking will take the weakest plane. Okay, cracking will take the weakest plane. Let me take a sip of my drink here. You guys guess what it is. No, it's nothing. Hold on. Cracking will take the weakest plane. If it hits aggregate, it will stop or be defected randomly. How about deflected? Or if it stops, it will stop or be deflected randomly to the next easiest path. Let's go right there. He said it will crack and then it'll go to the next easiest path. Coming back to my video, and I'm going to show this video, that he's saying, well, it took a crack here, and then the next easiest path was here, and then here, and here, and here, and here, and here, and here, and here. Let me see if I can cut to the chase for you. Look at this crack, all the way across here, and then across here. Well, his statement is that it finds, so this crack found one next spot, and wow, right to there. And then it couldn't find anything through here, so then it came here. And so some people, it put pressure on it, and it made it come out the other side. Well, no, I'm not going to say that yet. I'll give you a different version of that. And then it went down here and put pressure on this one, and you guys will see that this whole thing goes all the way down. Look what you're looking at. I'm going to give you a little scene stealer to where I'm going. So I think it would be more helpful now. These cracks are not random. It's from hydraulic loading of the truck unloading and offloading its fuels. All right, so it's loading and offloading. So I'm unloading, and loading the pad, and then offloading of the pad. Loading of the pad, and then coming off the pad. When it's loading the pad with its weight, it has more force than when it's empty. But nevertheless, it's still taking place. Look at these cracks. They're not random, guys. See how they come across and they keep going and going and going, and all the way to that one. As you can see, the cracks here, and then it comes out that side. I will show this in the video. This is not a random crack jumping from one spot to the next. This was loading of a vehicle, basically where my hand is, driving up onto the pad. And as it stops over many cycles, a few deliveries, not just all one day. And this is the pad, this is the crack that develops. And I'm going to talk to you about how you're looking at arches here. This is an arch. This is the other half of an arch. Look at the crack between the arches. This is an arch. This is another section of the, not dissected, it doesn't appear to be dissected 100% half. Nevertheless, it's still part of the arch. Another arch. Another arch on this side. Another arch here. That's an arch. That's an arch. All you're looking at is a bunch of holes in a concrete pad. Don't look at it as randomness. Look at it differently. These are holes in a concrete pad. Concrete pad was placed, and then somebody put these giant holes in the pad. These giant, perfect holes in the pad. And where did we go here? I'm trying to get to the... Good. Somebody put these giant holes in the pad. Of course, that's where the plumbing goes, the fuels and air and vents and things like that. Let me get you to the other end there. That didn't quite work out. Let me just skip. I'm scrubbing. Hold on, I might have scrubbed too fast. Bear with me. From this orange went to the left. Oh, that's right. I'm talking about the stones. I'll come to that. So the orange went to the left. All right, that's my angular thing. All the way over. Come on. Come on, dude. Step it up. There we go. All the way over to there. This is not one weak spot to the next weak spot. It's loaded on one side of the pad. Now, and then right here is the other side. This is another hole. The stresses of the pad resolve themselves. This truck is a tractor trailer, right? It's 80,000 pounds total, but it has a jackhammer effect of when it applies the brakes coming onto this pad, surging. Luckily, I got a truck at the end of the video that came on, and I was able to prove a point. How awesome is this? Watch this. Here's the truck. And as the truck stops, all those forces go to the front. Those forces aren't for free. This pad resolves itself, taking those forces onto the pad, the entire pad where the driver's side of the tire is. It resolves itself by loading the entire pad. It runs into this hole. It runs the forces around the hole, but it also has a counterforce, right? Everything has a counterforce. The counterforce of this circle, this radius of this arch, is on the other side. This is where they meet. This side meets that side. Beautifully so. This is one side meeting another side of forces. And this is where it's resolving. we're going to get, this is this pad in particular. Not all, it's not going to, you just can't say this about everything. So, but we're going, and I'm showing that, for example, this has no forces on it. This did not break. We are taught that you have to put expansion around this or it will crack. Not a single crack. How about this? We're looking at real fast. I want to give you guys scene stealers. Is that this has multiple points on it. Point, 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 around this thing, point, point, and point. Yet you see not a single crack coming off of this. Because the loads that are butting against this have all been equal. The load that hits anywhere on this so far has all been equal. And therefore there's no imbalance. There's no imbalance of equilibrium. I'm pointing at the points there. And we're going to back to this one here. Hold on, the one before it. Again, no expansion and yet no cracks coming off of here. Because all the forces around this are in equilibrium at this time. There's nothing surcharging it with the weight. Now, this is a larger hole as the one mirroring the one to the right. Same deal. There are no cracks because the forces around this are in equilibrium. Around this, they're not in equilibrium once upon loading with the vehicle. I think I might want to just give you a scene stealer and jump out his video and do more, but let's see. And so he says, yes, it is random as they are affected by the position of the random spacing of the aggregate. This is what we're taught as engineers, as contractors, that concrete is just a matter of when it will crack, that it's random. Well, it's not random. And even if you put expansion around there, it would still have cracked around that one side. Because the one side is not in equilibrium with the other side around the holes, the penetration. Cracking will take the weakest plane. If it hits aggregate, so it's not taking the weakest plane in this case with the pipes, the two of them are hitting each other. At that point, the equilibrium is right there as the least amount of equilibrium. Let's call it that instead of weakest plane. And now you see, there we have the crack. Predictable. It's not going to be random weakness. It's predictable weakness. It's predictable. It will stop or be deflected randomly with the L to the next easiest path. Ultimately, the break line will take the quickest and easiest path along the force line. This is, pretty close. It is also affected by heat, expansion, and contraction, and this is the fact. So it's not that whole pad. You can see that it's out in the open. It had the equal amount of temperature on it everywhere. Now, you look at those pipes, and you could say, well, the pipes create a different heat, etc. Well, you see where they are. The cracks are equal around there. The temperature will equal around the concrete, equally around there. So if it did have a different heat range, it was equal. If you look at it as hold on, my brain's frozen. Shoot, I had to pause the video. My brain's frozen. I want to tell you a path. Hold on. How about this? If you look at it as a load path, a free body diagram using heat signature based on what he states, you would see that, well, this is all equally heated and this is equally heated. Even if they had different temperatures, this metal heating at a different temperature than the concrete, it would still be equal around, and it would create a color pattern, if you will, of heat that would be hotter here perhaps and cooling out this way. But it would be equal all the way around in a radius. If anything, where the two heat paths would meet, you think right about in the middle there would create an issue, but then that would be one piece of spalling or something like that would pop up, which doesn't indicate itself as that at all. So I find that the heat as the issue is not an issue, except for during curing, heat is an issue. After curing, the heat's going to be pretty much even on this darn pad. I think internally I found some studies where they kept the sensors in the pads, and that was in post-tensioning study, believe it or not. So I don't like the way I said that, because that actually discredits you by saying believe it or not. I'm saying believe it or not. It's amazing that in the respect that we're talking about post-tension in the other videos, and that's not my intent to bring that up. It's like ironically is what I meant. So you can find, I think it's Texas did a post-tensioning study where they're a length of highway where they left the sensors in there. It was like 300 feet of it, or 300 yards, or 3 miles, something crazy. Well, they used transverse cables also, and they kept the heat sensors in there consistently for 1 or 2 years. And it's interesting to watch that basically the heat didn't do anything. All right, so the heat ranges are huge during the day, at different sensor depths and everything, and it was not a factor. So I state that the heat is not really, it's not a conclusive file. It's like 88%. That I state the heat is not your cracking. We're barking up the wrong tree at this point. Now, if you're going to go ahead and get a damn acetylene torch and put heat on the concrete, of course that's going to create a problem right where the acetylene torch is. All right, but I'm saying it's equally heated, so it's going to. Of course, you can dry out your aggregates, your moisture in your concrete sooner and cause a degradation that way. But that's an even degradation. And we'd have to look at some old highways that sat out in the middle of the desert and it's drying it out, sucking the moisture out of the concrete. Okay, and I have another one for you, Latitude, and so much I have. I just don't want to confuse people all the time. So if you look at block work, and then you look at the mortar between block work, and they add the mortar, and then they put the block on top, did they not just create concrete? There's the stone, which is the block above, with the different sizing, and then below is the block below it with the different sizing, and then they put a mortar bed between it, and they put the two stones on opposite sides. Isn't that a nice dissection of concrete right there? Aren't you looking at a macro concrete piece of concrete? And I give that to you. Ultimately, the break line will take the quickest and easiest path, right? It is also affected by heat expansion. Okay, this is what we're told. I can go heat up a damn pipe out there in concrete, and this will not cause a break. I've already done it. I'm not bothering with that experiment with you guys. It will not happen. You're not going to do that. You're not going to put a acetylene torch on a piece of pipe in concrete. It's not. It doesn't work. Maybe I'll show the video where I did that. I don't know. To prove a point. To prove a point, I'll show the video. Nope, it won't be good unless I do a new one. All right, so I say to you, I'm going to use. I have a piece of concrete that we all seen in other videos. So I'll use that one that's untouched. We saw the black paint on it. I'll put a acetylene torch on that metal pipe. We're going to heat it up, heat it up to acetylene temperatures. I'll use my flare device to get a range of temperature. And we're going to see that the pipe, let's see, I should have to heat it higher enough away that it's going to equally load the metal downwards and radiate downwards. And so it's not going to cause a crack. I'm going to show that. And I don't know, I'll take it to double, I'll take it to 200 degrees where we won't get that. And the concrete, we're going to measure the concrete temperature at not 200 degrees. How's that for an experiment to show you that this heat thing is also BS, mostly. All right. I mean, think of a dam. On one side of a dam, you've got cool water down below a dam. At the top of the dam, you have 100, I don't have to do the test now. You've got 140 degrees outside in Hoover Dam, for example. One side of the dam, 140 degrees. On the other side of the dam, you've got 50 degrees. You've got a 90-degree temperature range. How come it's not just cracking all apart all the way from the 50 degrees to the 90? How come you just don't get a full crack through? You're going to tell me because it's insulated, multiple layers of concrete and all this other stuff. I'm like, whatever, man. You got to get off of this. It can't, it's not true. I'll do the damn acetylene one. Your update video is correcting your comments expected. So he believes that this corrected it. I gave him a soft saying, you good. A pat on the back saying, I appreciate the banter. But now I'm showing you that I didn't really give him I'm just giving him the compliment of, at least you're coming at it. That's good. I'll give you this. Grout is not concrete. All right. No textbook will ever say that. Stop using the textbooks here. We're trying to design a concrete and determine how cracks happen. You got to get out of this concrete mode to do that. You're going to have to take new data on. Stop confining yourself with this concrete thing. Concrete is everything, right? It's a mixture of aggregates. You are going to tell me it's a certain concrete that has a different size, M30, M25 concrete, stuff like that. So different size stones. I already told you that you can make your own damn mix. You just need Portland and start making your damn mix, and you can call it concrete if you want. as long as it meets your specifications of concrete, and that will be a grout being able to take 10,000 psi, 2 inches thick, a cube. Okay. I tell you that concrete's not concrete. Who the hell rods concrete 21 times as placing it in a pad? I've never seen anybody do concrete 21 times. What's with this rodding of concrete? Put it in a test sample. That's ridiculous. It should be placed just as you would do in the field, which means people just kick it with their foot, scrape it off, now go test that sample. That's your PSI. Not rodding it 21 times. That's not concrete. No one does it. It's unfair. It's just stupid. No textbook will ever say not to add large aggregate. Well, no textbook ever says don't rod your concrete when testing it. All right, so that's just ridiculous. But then they tell you how to place the concrete, but no textbook says make sure you rod every section of concrete similar to the test sample 21 times. Place it in 3 layers and rod it. Come on. Come on, when you're being bedazzled and being scammed, realize you're being scammed. As this is a vital part of any mix. Yeah, well, P.S. I am not a mix expert. Okay, well then, you're not a mix expert. So you're just giving yourself a disclaimer against your own statements. I agree, but I know what I'm talking about. Now I say you don't know what you're talking about. Structural engineers specify the strength at 28 days. So this is called triangulation, guys. So to strengthen his position, he says structural engineers. Well, structural engineers is just somebody who just decided that they're going to be a little bit better dealing with structures and how load paths work and things like that. They're not nailing it. Structural engineers are still just civil engineers that decide to specialize a little bit, but they stick with their research and not coming out of their box and working out of the box, which I am doing with you guys now. I used to consider myself a structural engineer, but not anymore. I'm way beyond all this crap now. I'm not limited by this. I'm beyond the engineering of the limits that Latitude puts on himself and that the term structural engineer puts on yourself. Strengthens at 21 days, not the mixed composition. Unless it is a specialist item to look at rebar beams that are current. Well, no, you can specialize 28 days, a 7-day, a 3-day, a 24-hour. You can specialize. You can specify a many PSI difference in different ranges. Okay, and then they may specify with additives for a watered mix. All right. So now, structural engineers, you will not get a structural engineer crossing the line on adding an additive to any concrete mix. I have never found one. I wouldn't dare either. I use the concrete manufacturer, their expert at that plant, whatever plant it is, to tell me what he has tested his mixes at with their materials, etc. This is not, no structural engineer is going to make up a mix and hand it over and say you can now build a bridge with this. Not one. If they do, they're not acting in good faith as an engineer. It has to be tested, a tested mix. Tested mixes take 2 years. 2 years minimum. You're not going to get away with tested mix 1 year. You've got to go through all the cycles that you expect your mix to perform at. Vibration is important to get air out, as this weakens the unit. Hence, no sand. So air bubbles do not necessarily weaken a system, but although it typically weakens a system because it's voids. But remember, the void it created is what? An air bubble, yeah. All right. So I'm going to stay away from the air bubble because that's another long matrix of an answer with the hydrogen and the air, and this is not typical air. This is air entrained. I am not going down that line with this one. Let's play my video, and let's go ahead and wrap this video up. And let's start from here. This ties in for what my man is stating. 6 minutes long. Let me see how long this video would be. Let me pause it and see what I have here. 30 minutes. Okay. I think I'm going to do part 2 of this. I'm going to pause this, and it's just going to be part 2 of this.